welcome Professor Kyu-Jin from Seoul. He's gonna present now. He's also one of the co-organizers of this workshop, so I'm very happy to have you as a co-organizer and, of course, as a speaker of this workshop. And I'm really looking forward to your talk. Thank you.
Okay, thank you. Pick my title of talk as Design Software Robots for Unmet Needs of Smart Living. I'll be talking mostly about technology for people with disability. I use the word smart living because people with disability. But when you say smart living, it's mostly for people without disability. But I think people with disability has the right to live smartly. And I put the subtitle called Requires Minimalism in Robotics because I'm sure if you were at Professor Hirose Sensei's talk, if some of you were there, he was showing a review that his paper got rejected because there was no control and sensors, even though the robot was doing what it was supposed to do. So I think it rhymed a lot with research that we are working on, because there are things that are very simple, but it gets work done, and it doesn't exist. It does, and they're struggling because those kind of research in terms of like technology. Somebody were talking about the funding, right? We cannot get funding with those kind of research, and it's hard to publish a paper with that. But we really would like to see those kind of things. So I have many slides, but let me go like really quickly. I'll just go through some of the technologies that we're developing. But I have to start with introducing Professor Sang-Mook Lee, because I got into this technology for disability because of him. He is a professor at our university. He got injured on a field trip. He's an earth scientist, so he goes on to a field trip and he had a car accident. So he is now a C4 patient, means that he cannot move any part of his. He can only move his head and arms, but he started teaching a year after his accident, which was a very big news in Korea. Because normally when people get in car accident into this kind of shape, in Korea, they would be in hospital for years and years. But luckily, he got injured in US, so he had got in the hospital. I forgot the name of the hospital, but what he said was that hospital didn't try to heal him, but they taught him how to use the assistive technologies. They got him these like expensive wheelchairs and the mouthpiece, like what do you call, mouse controller and those kind of things. And that inspired one of my professor at my department. He had won a very big award, 100K award, and he donated the money to him. And the awardee of that award knew about it later, so they gave him another 100K. And he again donated the money to create a small group of working group for professors to work on technology for disability. And that was ongoing. And the guy next door to me, the professor next door to me, asked me to join a dinner. Come on, let's go. We have a free dinner. So, free dinner, right? As a student at MIT, we used to go to free dinners a lot. I went to all kinds of free dinners. And again, I went to the free dinner and they told me, hey, you're a roboticist, so why don't you work on, like robots to help feed the people who cannot use their arm. So, okay, sounds like a good idea. So we started working, on this, and we started meeting people with a disability. And what I found was he's a C6 patient, and he told us, I don't want a robot to feed me. I don't want somebody else to feed me. I want to feed myself. Only if I can use my hand. And that's what I found, that 50% of the people in a wheelchair cannot use their hand. There are a lot of people who can use their arms, but not the hand. So they somehow, do things without their hand, or they will need helpers to actually, let them go around. And This was back in 2008, 2009. So at the time, most of the wearable robots were rigid wearable robots, and they're not going to use it. So that's when we started thinking about creating we went back to the basics. So why is this wearable robot so bulky, and it's because of the frames, right? There's these frames on the wearable robots. Do we need a frame? So that was the original question that we asked ourselves. Hey, come on, there's bones. Bones can be frames. Why do we need frames? So let's remove the frame and just use tendons, because it's the tendons that people cannot control, the muscle and the tendons. So instead of using these kind of mechanical components, let's use fabrics. So that was the beginning of our journey into the soft wearable robots. We originally called it frameless exoskeleton. We published our first paper with the title frameless exoskeleton, but now we call it like soft wearable robot and we call it exoglove. Okay, so that's the history. Oh, it's good. So this session allows me to talk about these things instead of the technology. So yeah, so exoglove, came out. Hyun-gi, he was the original developer. He had a hard time because he kept on asking me, "Is this a robot? Are we building a robot? Is this a real robot?" So we have 3 sewing machines in our lab. He was sewing, cloth fabrics. Am I building a robot? That was. But now everyone calls it a robot, so that's good. So it's exoglove made of fabric. So we published this at RAM. Exoglove, and we also tried to look into issues of so basically, as you can see, it has under actuation. So we wanted simple control. So we used only one motor to drive 2 fingers, and it adapts to the shape using under actuation mechanism. So it's special under actuation mechanism designed to be inside the glove. If you're interested, you can read the papers. And then, well, we met like people and they were saying, oh, we cannot use it while during bathing, cleaning if something gets dirty. So hygiene is an issue if you use these kind of fabric. And that's when we started thinking, as a robotist, we are always more concerned about the functionality of the robot, but in order for people to use it, it's the usability that's very important. So can you use it for all these kind of different cases? If not, they're not going to use it at all. They're not going to use it just for single functionality and then take it off. It have to be for everyday life. So to truly assist disabled, we need to address all these kind of issues, weights, there's mechanical performance aspects and there's also usability aspects. So there's so many requirements to meet. As a roboticist, we are not used to, meeting these kind of demands. But anyway, so we actually came up with another design, exoglove poly. We changed it to polymer because of the hygiene issue. So people wanted this to be easily washable and those kind of things. We reduced the number of actuators by changing the thumb. Thumb was an active thumb, but we could do a lot of things with just a passive thumb. So made the passive thumb. So, and then made it easy to wear. And it has to be, instead of putting it into the glove, we had to make it easy to wear. So we created this kind of strap mechanism. So we had like tendon anchoring supports, paragraphs. So this was back in 2015. So we had this, and we had to think about the safety. So we shielded the wires, covered the wires with Teflon tube. Something not important in the paper, but important in real life. So it had to be adaptable to different finger lengths. So we created these kind of designs. So it's stretchable. So also we had under actuation mechanism, the same mechanism that we used for original exoglove. And we also built what's called a dual slag enabling actuator. We also developed what's called slag enabling actuator, because when you say tendon drive in robotics, all the tendon drives are used in mostly in surgical robots where you have you can maintain tension all the time. You need to apply pre-tension to have a fast response. But if you do that on a human hand, pre-tensioning on the human hand, that's going to be terrible. And if you don't have pre-tension, what's going to happen is all the wires are going to start to come out of your pulley. So we had to develop this kind of mechanism. We call it slag enabling actuator. If you search for that, there's a paper about it. Oh, so we had this video made. Hong Chong. He's been testing our exoglove poly, but he's still not using our glove. But we're still working on it. You saw the button, so we had him try, EMG. We had him try different things. We also had like a switch and everything, but he liked the button the most. So simple enough, right? So we gave him the button. So it was waterproof. So he could use it for like in the bathroom. It's easily like washable. So wow, I can talk about this like proudly in this session. That's really okay. So opening a door, enhancement of mobility. It doesn't. I mean, they cannot open the door. That means they are not mobile, right? So they need somebody else to open the door. But if they can move their hand, now they can open the doors by themselves. So we also looked into the problem of intention detection. Like I said, there's biosignal, mechanical, and it needs calibration, needs additional actions. So what we came up with, we proposed a new paradigm of using cameras for intention detection. We called it VideoNet. So we published it. Why isn't this? So it's eyes are faster than hands. That's very similar to a title of one of our movies, actually. Not a title, but one mention of the movies. But what we did was, instead of using any kind of biosignal, you have a camera that he's wearing, and then he's looking at his hands, and we tried to find if we could do intention detection with that. It worked very well. We were quite surprised. And what we found was, because we were comparing our work with those robotic hands with cameras and then trying to grasp things, we thought it would be a very hard task. But what we didn't realize at the time was people can use their arms. It's the hand that they can move. So all we needed to do was to find the right timing for this grasping. So basically the intention was already embedded in his hand movement. So that's why it was so easy. We were able to detect when he's about to grasp. We make it close, and then we also detect the ground and everything. So when he puts it down, it opens up. Simple as that. So we worked on that as well. So that's published in Science Robotics last year, the year before. But here are some of the things that we also did. It's called Grip It. No motors. It's just very simple string. You pull the string and then you tuck it. But what it can do is it can do a tripod grasp. Tripod grasp is a grasp for holding pens, because there are assistive devices for holding pens, but what it is, you have a attachment next to your finger. So you either do something like this, or you have like this big bulky thing that has like a rigid things. But here what we did was we just created a simple tendon routing. So with that tendon routing, he could actually do a tripod grasp, and good for holding pens. And we are actually measuring how long it takes to wear. Wearing time is very important for people with disability. If it takes too long, they're not going to use it. So we actually tried selling this on a crowdsourcing in Korea. We sold 3, I think 2. So we failed miserably. But still, I think I wish, I still cannot figure out how to do this, but we think this is very good, and it should help people who cannot use their hand if they want to hold their pen with like a right, close tendon routing with a right tendon grasp. We also developed like motorized version and all those kind of things as well. This is another work that we worked on. It's called Exoglove Power. This is a exoglove with a intention detection of an EMG, but this is a special EMG where when you say EMG-based intention detection, people, try to estimate if it's making, paper, scissors, rocks, or very complicated movements. But what this does is we have just single EMG, and we found out that if you attach this EMG at the right junction, you can very robustly estimate whether the person is trying to do a power grasp or not. Simple as that. So very simple, very robust. So we used it to for like creating this kind of glove. Also, it's published in TMRB. So this is the sort of a mechanism of the SLAC enabling actuator. It basically has a one-way clutch and a spool, and that's it. And you can actually prevent the tangling of the tendons inside the motor. We also developed another actuator called slider tendon linear actuator. What it is, like if you, some people use linear actuator to avoid that kind of entanglement, but linear actuators are really big. What this is it sort of mimics the linear actuator, except that it uses these slider tendons. It's very simple. And I think the biggest benefit of this is we made this part easily detachable from the actuator. So before, even the SLAC enabling actuator, all the tendons were connected to the motor, and then we had it connected to the glove directly. But with this, we can now easily attach and detach the tendons. And then I have several topics to talk about. Can you please let me know the time that I have left? Maybe very short time, right? Right. So I know. So I mean, so this is kind of, I guess, the way we do research, I would say. So for example, we have a software robot for respiration. So respiration is very important. And we also found, I'm not sure if you can hear this. Let's see. So he's a Korean singer. So he cannot make a sound, but if his dad pushes his belly, he can actually make this kind of sound. So we said, okay, let's make a soft wearable robot for, okay, I guess I have to, okay. So, there are many wearable robots for the limbs, but not for interacting with internal organs. We need wearable robot that can interact with the internal organs to, help with the respiration. There are some breathing helping, what do you call belts, but they don't produce enough force to be able to do this. So we call it ExoApps. It's a human assisted wearable robot for internal organs. Sang-Yeop Lee actually worked on it. So it's a lot smaller than the original versions. And this is how it looks like. It's basically a belt with a backpack with motors. And it actually, we have a stiffness design. So you can see the joystick. He can drive his joystick with, and he can actually help his belly so he can make a sound. So, but actually he's not using our device because he actually asked us to give him his device, and we didn't have any approvals or anything. So it's to go through those, to go through that kind of whole process, it's really a lot of money is needed. And so right now he's using something made of a very rigid device, which his dad made. Actually, his dad didn't make it, somebody else made it, but they made it that his dad made it, so there would be no responsibility issue. But anyway, so we hope this technology can be evolved even more later. So we worked on this kind of modeling, effort synchronize, assist scan. So this is all about. So we wanted to have automatic synchronization. So with the breathing, so it can help with the breathing, it can help with the coughing, it can help with singing. So I think there is quite a lot of people who needs these kind of breath assistance. I didn't know that this respiratory rehabilitation is a big area. I got to know it when I visited Italy, world's oldest rehabilitation hospital. And 1/3 of the rehabilitation was respiratory rehabilitation. So that means there's still quite a lot of need in there. And there isn't much technology there. So we hope this could do something. So what he's working on is we put a sensor and then monitor the breathing and then do a synchronization with the robot. And it's okay. Coughing is very important because if you don't cough, he has to cough once or twice a day to get rid of his mucus. Otherwise, his mucus is gonna stay there. So what normally happens is a person assisting him pushes his belly once a day to get the mucus out. So we're hoping like this kind of device can be used in the future. Also, we had one patient who cannot actually speak, but he cannot normally speak. He cannot speak because he cannot make a sound. So this lady came to us. She was actually like pushing his belly with her feet to make him make a sound. But so like using our device, if we synchronize it correctly with his breathing, he could say 안녕하세요. That's like hello in Korean. We're still on a very primitive stage. We've been in primitive stage for a very long time, but we hope that can be developed. So we also worked on some lift assist. I think there's many people working on lift assist as well. Our approach was to sort of create a environment in around you. So instead of using motors, we are using just passive component of a muscle. So there's a science paper about muscles, how animals move, and that paper says the muscle has 4 functions, not just actuation, but it has like other, and we said use those to create a new motion pattern on the environment. If you're in the water, you move differently, right? So why not create, so muscles are used as motors, springs, brakes, and struts. So we think when you say muscles are only motors, but if we carefully use the springs, brakes, struts, we could do something useful. So that's why we created this suit. We call it movement reshaping suit. If you wear this, the reason that people get injured is because they are doing like this instead of doing this. They should be doing squatting, but they're doing this because this is easier and more comfortable. So you're trained to do this, but you forget and you keep on doing this and you get your. So what we did was if you wear this, actually, we had actually a demo at our exhibition. If you wear this, the impedance map changes. And by changing this impedance map, what you can do is you can only bend your waist only if you kneel. So by doing that, if you wear this, you will feel high impedance when you're kneeling, but if you kneel, you will feel low impedance. So that's why we call it body-powered variable impedance. So it's a squatting motion is needed, but that's what people are doing. So we developed a movement reshaping exosuit. See, there's an article about this in IEEE Spectrum. You can read about it. Also, this is not soft wearable robot, but we are also working on prosthetic hand. I know. Do you know that the winner of the first the challenge? What's that challenge? I forgot the name. This ETH. What is it? Cybathlon, right? Cybathlon. The winner of the prosthetic hand was body-powered prosthetic hand, not the motorized prosthetic hand. And most of the people that needs prosthetic hands, 90% of them, at least in Korea, they use non-moving fashion prosthetics. There's very few people who are using these motorized prosthetic hands. Why? It's heavy, it's expensive, so many issues. So, cost is an issue, right? Cosmetic issues are cosmetic prosthetics, 4,000, body power 10,000, myoelectric 2,200K. Of course, if you can somehow get insurance, maybe, but so weight isn't also an issue. Body part ones are very very lightweight, 120, 200 myelectric, 450 to 750. So we want a suitable foldable prosthetic hand. So our approach was we wanted to build a 3D printed prosthetic hand, but there's so many 3D printed prosthetic hands, except you print the parts and then you have to assemble everything, right? That's the 3D printed hands right now. What we came up with, you don't have to assemble. We created a joint that you can 3D print and you can move. So it's based on the bio-inspiration. It's using the MCP joint. Our bio-inspired printable joint allows us to print a joint that does not have a gap. You can print a joint using 3D printing, but if you can see that on the exhibitions that there's always gaps. It doesn't work well. But using our design, we initially print it as a gap, but then after you move it into the operation workspace, there's no gap by using the cam effect. So this can be 3D printed. And this is the hand. So, I mean, if you just look at the hand, it looks pretty similar to other 3D printed hands. But another thing that we found was from the feedback from the users was this is light. This is about 60 grams lighter than the other 3D printed hands because there's no joints. You know, those little axes, if you collect all the axes, that's about like 60 grams. And that small weight difference is a big difference for people. So they liked it. We still have to work on, making this more robust. But another key point that we are thinking about this is once this is easily 3D printable, that means we can have so many different designs of this online. And then you can just click and download and print. Right now, there are like open source 3D printed hands, but you have to print them and then you have to assemble them. Maybe you can use high school students to do that, but you need, like 3 hours, 4 hours of labor to do that. And you need to learn how to do that. But I think this could change, things, how a lot of things. And I thought this was a very, very good research. We submitted to Science Robotics. It got rejected. Too simple. But I believe this has a very potential for high impact. It could change how we print prosthetic hands. And if we could create this kind of a platform, where we have all these different kinds of hands, customization is a very important issue in these kind of technologies. People want their own, what they want is not a very well-functioning, but something cosmetically that looks good for them. So I think using this technology, there could be a more potential for doing that. Also swinging, a lot of leisure activities are involved with swinging, right? Rackets. But current technology is this. You gotta have like this kind of, you see that? You put it in the hole, grip. That's the current technology right now. So many people are working on prosthetic hands that can do this, that, and with like 24 actuators, but there is no prosthetic hands that look like a hand that can hold a racket. So we started working on, so the difference between, I have to check, but this is what Oliver Brock told me. He said the difference between human and the gorillas is that gorillas cannot do this. Humans can do this. So I can, gorillas only can do this. So that's what we did. We built basically, if you look at your palm, right, you have several bones, metacarpal bones, whereas all the prosthetics, it's made of a solid, single palm. And on top of that, we use differential mechanism. So we use only 3 actuators. So you can actually grasp this very firm, like firm grasp is important because swinging, a lot of heating, right? So it has to be firm. So our goal was to build a prosthetic hand that you use only for single tasks like golfing, tennis. We started with golfing because I like golf, and I think golf is considered a luxurious sports in Korea, but I think people with disability has a right to play golf. So with like real hand-looking prosthetics. So we started working on it. And also wrist is important. It has to be released at the right timing. So together with KAIST, we also developed a release mechanism that releases at the right swing temperature. So we initially tested it on a swing machine. There's I think we got this right after like 10 unsuccessful. And then we haven't actually been able to test it on people with a disability, but we tested it with a normal golfer, with an extra arm, and then we did that. And we are also, tennis is also one sports, right? And so tennis, the difference is you have to lock your wrist at the right time. So we also built something like this. Tennis and also fishing also requires a racket. So we also built a clutching mechanism that actually clutches at the right timing. And we also have that kind of result. So human body, I mean, it has like over 600 muscles, 4,000 tendons, 900 ligaments, and there's so many different motions that people need. Right now, we have these kinds of humanoid robots, that seems to be doing everything, right? But there's so many things that cannot be done. We need a lot more different technologies that can do so many different things. And I don't think there can be just one technology to help everyone. We need very, very customized technology to meet, all different kinds of needs. And the issue is market is so small. So there's no business model for, to meet all those needs. So I guess the question is, how do we meet those demands, right? So I tried to write, so I think, technology to be used by people to improve their living requires more than functionality, but there's no systematic methodology for, this kind of designing to meet these demands. I don't know, not at least in the robotics area, maybe in the design, right? So maybe we need more UX experts, I think, in robotic society. IT is very big on UX. User experience is very, very important in IT. If you think about like mobile phones, like 10 people gather together to remove just one button, one click. And robotics is we just add one actuator without any guilt. Just, okay, we need one more actuator, add one more actuator. Oh, one more sensor, okay, one more sensor. Where IT people are doing so much to just remove one click. So I think we need to do something here. We need something that motivates us to do that. And I think minimalism in robot design is very, very important. And finding product market fit is also very, very important, because to solve the real problem, we need our products to be in the market. And it's not just about technology, it's product market fit and the business model. Google makes a lot of money by just people searching online, right? Why can't we have a business model for something like this? Like, there's so many things that people really, really need, instead of just searching for, what any like those kind of stars are doing, or there's so many things. But I'm also talking to business model people, and they're telling me people are more interested in fun than functionality. So maybe we should somehow connect our technology with fun more than functionality, right? As a roboticist, we are more interested in the functionality, but fun is what gets people spend their money. So maybe that's one thing. And one other thing that we are working on is wearable hands for children. And I find that demand is like 6 times higher, because hand for like elderly people, only it's that person that has the pain, and sometimes he doesn't care, oh, I'm okay with not moving my hand. But child, it's not just the child that wants his hand to move, but it's their mother, father, grandfather, grandmother, wife's grandfather, wife's grandmother. So 6, you have 6 people who want his or her hand to move. So we're trying to we think maybe that's where we should start. But now the technology is harder because the hand is so small for children. The size is so different, and it's so hard. That's the bottom line. It's a very, very hard. So I mean, there's many students that comes into this field of wearable robots thinking it's cool, but it's so hard. So I tell them, oh, you have to, it's really hard. So you have to be ready to do all these kind of things too, if you really want to do a wearable robot that can impact. So and soft robotics community, I really appreciate Cecilia is there. I really appreciate like our community. I think building a community that has like similar thinking is very important. So I asked Jan to build a TC on robots for humanity, so we can create a certain community that thinks in the same direction and collect people, publish an article, do a special session, and so that people won't reject our paper because it's not like technology oriented. That's what I think what soft robotics did, right, Cecilia? Like originally soft robotics papers were getting rejected because there's no modeling, and now with a big community, and I think it's going there. So I think, we need this kind of community building to actually make the change. And also I have to thank all my students who's worked really hard, without really knowing where they're going, because I didn't know where I was going, but now I have a clear, much better goal, and I know what the issues are. I still don't have the solutions, but at least I know where I'm headed. So thank you very much.
Thank you so much for this great talk. I think you are tackling very important problems with a lot of, very important problems, and I can really understand that they are hard to tackle and that there are a lot of challenges. Okay, let us thank the speaker again. And now it's my great pleasure to introduce Professor Helge Wurdemann from University College London. He's the head of the UCL Soft Robotics, Soft Haptics and Robotics Lab. He's co-director of the Intelligent Mobility at UCL, and he's the co-general chair of IQA 2023. Helge, stage is yours.
Thank you very much, Jan, and thank you for pulling together all these interesting speakers and panel members today at IROS 2022. And it's a pleasure to be part of this. And as you said, I'd like to present our work that we are doing on soft, smart, stiffness-controllable robots and sensors. And I want to give you two examples of work that we are aiming for. So we have two applications here. On the left-hand side, abdominal robotic minimally invasive surgery. So there I will give you the example of colorectal surgery, but also show you a future application that we're aiming for in collaboration with Professor Christian Durier from Lille University. And then I will shortly talk about the work that we do in robotic interventions, and mainly focusing there on transcatheter aortic valve replacement. We all know this fantastic work from Professor Ziyu Mori, who built this very small soft robotic manipulator or actuator of not only 12 millimeter, as you can see here, but he scaled it down to a diameter of 4 millimeter. And this is really the inspiration that we took as part of the StiffLab project, which was run by and coordinated by Professor Caspar Althofer from Queen Mary University of London, aiming for an application of soft robotic for soft robots in total mesorectal excision. And here you can see the information and the application that was provided at that time from Professor Alberto Arezzo. So you can see trocar ports that are fairly distributed over the abdominal area. So it's very widespread, and through these trocar ports, rigid instruments have to cover quite a wide range of workspace. The aim of this operation is to not only separate the surrounding tissue of the colon along the colon, but fundamentally remove the tumorous cancerous tissue here, and then suture back the rectum to the colon. So you can see that there is a quite wide workspace that needs to be covered through these trocar boards. So what we proposed in this project, and I'm sure that many of you are familiar with this manipulator, which was developed in collaboration with SSSA and Ariana Menchassi's, Professor Ariana Menchassi's team. A manipulator which has a cylindrical form and a number of actuation chambers that you can see here. In total, 3 pairs of actuation chambers that are individually reinforced using a fiber to restrict axial expansion and only allow elongation. And through this elongation, you can then achieve bending behavior, but also if you actuate all of the chamber pairs simultaneously, you can achieve bending behavior. So the fundamental difference to the robot that I showed earlier on in the slide is that these type of robots have a working channel in the middle. So the surgeon is able to push through, for example, an endoscopic camera, but also other grippers and tools that are needed for the surgery. So we then assembled, as you can see here, one of our first miniaturized robots, 2 segments here. You can clearly see how the pneumatic piping is feeding the pressurized air to the tip module here. The inner channel contains an endoscopic camera. So there's a working chamber inside. It's a miniaturized size at that time, below 50 millimeters. So we can use commercially available trocar ports, but ideally we would go beyond 15 or 12 millimeter, in fact, because as you can see here, the Da Vinci tools that are commercially available are even going down below 10 millimeter in diameter. So then we went to the University of Dundee and we had the opportunity to demonstrate some procedural steps of colorectal surgery on human cadavers, as you can see here. And our surgical team went to the university and performed a number of procedural steps showing the advantages of a flexible soft robotic tool, and in this case used for vision. The reason why we were able to miniaturize our robot at that time below the diameter of 50 millimeter was in fact that we reinforced each actuation chamber. So we very much started with the diameter of 25 millimeter with the robot on the very left-hand side, where we had a lot of ballooning effects, and these ballooning effects were contained through a braided sheath that you can see in the middle. But in fact, this external constraint of preventing ballooning had some effect on the sensing devices, but also on the miniaturization of our robot. And this reinforcement of each fiber really brought us to a diameter of below 15 millimeter. However, we were not able to go very much below 50 millimeter due to the fact that we used circular shaped, cross-sectional shaped actuation chambers. So in our work here, we investigated how can we change the shape of the cross-sectional chambers. For instance, have a semicircular cross-sectional geometry, as you can see in our robot here. This should be type 2 robot. And then also understand what the performance of a robot is that has different cross-sectional geometries compared to the robot that I just showed in the video earlier. So we have fabricated these using injection molding. So we have used a very similar technique that we used that time in our StiffLock project to fabricate these. And fundamentally important here is that the area of the actuation chambers in total remains the same, or at least very similar in this process. So then we understood through characterization what the bending and elongation behavior is using exactly the same elongation ratio. And you can see here in the figure that the robot with the circular cross-sectional geometries is able to only bend to about or is achieving the same bending angle at a lower pressure, at a higher pressure compared to when we use a semicircular cross-sectional geometry. Then we also understood what the workspace of these robots are, as you can see here. And again, for cross-sectional geometries that are semicircular, as you can imagine, the workspace volume is slightly larger compared to the circular cross-sectional space. So this is a summary of all the experiments that we have performed with this regard. And you can clearly see here, when we look at the bending ratio and the bending capability, when all three chambers are actuated, or when one chamber is actuated or two chambers are actuated, the type 2 robot, which has the semicircular shaped cross sections, can outperform the one with circular shaped actuation chambers. However, when we look at the stiffness results on the right-hand side, so this is experiment 4, we can see that between 20 to 25% less stiffness can be achieved with a robot that has semicircular shaped actuation chambers. So now I mentioned that both of these robots are still 14.5 millimeter in diameter, but you can see here in this video here that we can now even go lower than 12 millimeter. In fact, in our lab, we fabricated robots that are 8 millimeter in diameter and then have a 2-segment robot. So this way of having different shaped actuation chambers and go maybe into semicircular shaped cross-sectional shaped actuation chambers will allow us to drastically miniaturize these type of robots, keeping an inner free channel for tools. And one of the future tools that we want to investigate are tools used for in vivo cancer imaging. And there we work with Christian Durier to deliver a 2-segment robot that allows to use the technology of mass spectrometer data so that cancer tissue can be detected in living tissue during an operation. On the other side, we are also concentrating on cardiovascular interventions. And there we focus on a fairly young intervention, which is called transcatheter aortic valve replacement, which very much started as a procedure in the early 2000s. This procedure is treating aortic stenosis. And aortic stenosis is a disease where the valves of the aortic, the leaflets of the aortic valves calcify. So when they calcify, the aortic valve cannot open and close properly. So you have blood flow that is not undesirable. This can have many causes, and the best way to treat it is, of course, open surgery and implant a mechanical valve. However, about 30% of patients cannot undergo this surgery, and therefore transcatheter aortic valve implantation or replacement, TAVI or TAVR, is a suitable solution for them. What is being done in this type of surgery is that a balloon catheter is inserted into the femoral artery and pushed up the aortic vessel towards the aortic valve. And inside this aortic valve, so you have to see that this is a calcified valve, and the balloon is expanded. This is a device called a valvuloplasty balloon, and this valvuloplasty balloon is used in a manual way in surgery or in the operation. After that, another balloon catheter is used, and a bioprosthetic valve is mounted onto this balloon, and then it is inserted again into the femoral artery and pushed up towards the aortic valve, and then using a balloon, a valve is deployed on top of the native valve. Of course, there are also other valves which are called self-expandable valves, so there's no second balloon required to expand the valves. However, in many cases, cardiologists will use a balloon on top of the self-expandable mechanisms to really mount the bioprosthetic valve on top of the native valve. I'm very interested in this first procedure, which is called valvuloplasty, where the balloon is expanded and essentially breaks the calcified leaflets. Of course, there are technologies, imaging technologies, that would take preoperative imaging to assess the aortic valve and the leaflets, and assess also the diameter of this to have an indication of what the diameter should be, or the circumference should be, of this bioprosthetic valve. However, due to the fact that during valvuloplasty, the entire shape of this aortic annulus is changing, the size sometimes is not optimally determined, and there are leaks happening. So leaks are either happening through the leaflets when the valve is opened too much, for instance, or between the annulus and the bioprosthetic valve, and that can result in the patients to get a pacemaker, which drastically changed their life. When we look at all the imaging technology, for sure, there are two disadvantages. The first one is that because of the change after valvuloplasty, the diameter cannot be accurately determined. It only gives an estimation. But on the other side, there's no information of the level of calcification of the valve and the leaflets. So the mechanical properties are not there for the cardiologist. So we have developed this actuation system. So we're using a commercially available Edwards balloon, which is mounted to this syringe pump, which can rapidly actuate this balloon catheter. And on top of this, we can monitor the pressure. So now, this is a part of our previous platform. Now, when we actuate this balloon, we can measure the pressure depending on how much volume or how much water essentially is pumped into this device. And you can clearly see, if we talk about a free inflation, at one point there is an increase, a significant increase in pressure when there is tension of the material that the balloon catheter is made of. So now we have fabricated idealized phantoms. So on the one hand, we have manufactured rigid idealized phantoms that have a different diameter, but also a different length, which is, so there we have taken data from medical papers to replicate the geometry of annulus. But on the other side, we also have fabricated and printed, in fact, compliant idealized annular phantoms. Again, these stiffnesses are very similar to the stiffnesses of a calcified aortic valve. And then here you can see results that we have obtained experimental when there's a constrained environment or the balloon is inflated in a constrained environment within our idealized phantoms. So you can see on the one side that these pressure volume curves, so these PV curves, are deviating from the standard free inflation curves at an earlier point, as you can see here, when we change the diameter of our idealized phantoms. But you can also see that the slope of the PV curves are changing depending on the length of the annulus. So there is a way to get more information about the circumference or the diameter of the annulus, but also the length of the annulus to understand where exactly the bioprosthetic valve needs to be implanted. So now we have also developed a model apart from our numerical model. We have looked into, and these numerical models are really our gold standard in a way, but we also looked into real-time analytical models, and these are based on a thin-walled vessel, as you can see here, to derive the relationship between the amount of water that are transferred into the balloon catheter and the diameter of the expansion of the balloon. So there are a number of parameters. Some of these parameters can be determined using the material properties, but also the geometry of these balloon catheters. So you can do a material characterization very easily for all the balloon catheters. So these can be compliant or non-compliant materials that they are made of. But then we also use the free inflation curve to calibrate a number of other model parameters, as you can see here. And based on this, we then have implemented a sizing algorithm, and the sizing algorithm really makes use of the deviation point at which the PV curve deviates from the free inflation curves that is very characteristic for each of these balloon catheters of different diameters, of different materials. So now you can see that, of course, in idealized phantoms, these gives us a fairly good estimation of the diameter of the annulus. And I have to say that our way of measuring the diameter is not meant as a method to replace preoperative imaging data, but really gives a confirmation and decision-making tool to the cardiologists when selecting different bioprosthetic valves of different diameters. So now there's more work to be done in this area. On the one side, I mentioned that we are looking into idealized phantoms of annuli. When you look at annuli geometries, they are usually not circular shaped, but they have an elliptical shape. So how can we develop future balloon catheters, which are fairly easy devices, in order to measure the level of or the two different diameters, essentially. But also, I mentioned that data of the mechanical properties of the annulus and the level of calcification is missing. So we are looking into how can we develop sensors that can be implemented on the outside of the balloon catheters that gives us force information that are acting on the tissue. And then at the same time, our model will give us displacement information to then have an idea of the level of calcification of the aortic valve. So there's many different type of works. I very much like this work on cardiovascular interventions, because it makes use of a device that is already commercially available, approved to be used in the operating theater. And based on data processing, we are able to give more information to the cardiologist that inform him in his or her decision-making process. So I very much like to thank the team that is currently working with me on these projects, and of course the funders who have so far trusted us in doing and delivering our work. And I thank again the team and the audience in Kyoto and online for listening. And I hope that after today we will see us in London at ICRA 2023. Thank you very much.
Thank you so much, Helge. One thing that I wanted to mention is that Helge was also one of the co-organizers of this workshop, like Annika said in the beginning. So he also helped a lot, putting this great event here together. I'm really thankful for this. It's a pleasure to work with you. So let us thank the speaker again, and then I will lead you into the coffee break of 10 minutes. Thank you.
Thank you very much. Yeah.
I think now we can start with the session 2, part 2, which is soft robots for humanity. But for this first presentation, we have Dr. Shahram Eivazi from FESTO, and he is also working as a research scientist at Tübingen University in Germany. So he will talk a little bit about bionics for education. So I think that's also a very interesting topic. And Shahram, if you would like to share your screen, I think we can start with the presentation.
Right. Thanks for introduction. Okay, thanks for introduction. So I jump quickly because I heard also you're a little bit behind the schedules. So today talks, I will discuss about our projects and our activities in the topic of soft robotic from the industry perspective. And a brief introduction. So my name is Shahram, and you're right, I'm a group lead at University of Tübingen, but actually I am an employed at FESTO as a researcher. So we have an industry and campus program between the company called FESTO and University of Tübingen. And this is basically activities that we do both from the industry and research and try to find a common interesting area for both sides, one from the scientific perspective, another one also from the company and business aspects. And the small introduction about the FESTO for people who are not aware about FESTO. It is a family owned by company. So it is, we are having about 20,000 employees worldwide. So it's large enough. And then we are located in the Stuttgart area. This is about FESTO. The main business or the main activity of FESTO as a company is actually an automation company focusing on pneumatics and automation within the factories. So this is about 100 years where the FESTO is involved on different automation systems. Today, I'm not going to discuss with that because that's not something that is relevant to the topic of this workshop. As well as, of course, we have also a lot of training and deductive part for industry. This is two main activities. But more interesting for what is important for our today workshop is that the FESTO has been for many years, over decades, on the topic of bionic and bionic animals that we have been developing for many years. And you can see some of the picture here. And yeah, for audience who are interested to later look to it, just Google FESTO and bionic, then you will see different videos in YouTube from many years ago. We have built various animals in this topic. Then for the soft robotic applications, that has been one of our kind of passions to go forward. We have been looking from two perspectives. One is for the human-machine collaborations that we want to enable, for example, robots or mainly robots to be very close to human. And of course, soft materials is very appealing for this perspective. From this perspective, is very safe and lightweighted. And then at the same time, we want to be able to provide some kind of intelligent systems or applications for these soft robots that they can do, and for example, helping humans during their everyday work. Before I jump to the bionic for education, I will first show you quickly a few of our examples of the soft projects, and then I will move to the bionic for education. So one of our kind of first and large project was the BioInspire soft arm. Earlier, we got inspired from 2009 working on the soft arm based on the elephant trunk. So we have built various, let's say, version of the soft arm. You can see in these pictures from 2009 until now. Based on different inspiration and trying to use different technology and like mix them together and try to use to make an basically application out of it. In all cases, a lot of focus has been on pneumatics. So technologies that have been used in the arms are mainly blowers and with airs and the joints that can basically pneumatic joints that they can rotate and pneumatic drives. This has been until now, even though recently, very recently, we have also new arms that are not pneumatic based and they are also soft, but I did not add that for today to just keep the presentation short. You can see in these pictures, this information is also available in internet, so I will not go much in details on the technology part, again, to the fact that I have a short times for today's presentation. Then another part that it has been used a lot in industry, at least, it has been the soft grippers. So you heard and you hear everywhere different type of ideas for soft grippers. At the moment are also in market, including different FESTO soft grippers. I think we have over like 3-4 of them. But for example, today I put here, for example, octopus gripper, as you can see, inspired by an octopus that can, hold an object, for example, a pipe or a cup or a bottle of water easily. Here you can see how that look like. And then the other example was that we inspired from chameleon, that we say we could have an grippers that can come down and like grab the object by itself or suck it and bring it inside. This is also at the moment in the market. So the previous gripper is something that very rarely is used if somebody really needs it for a specific application. But this gripper is much more available and people are using it in industry for different purposes. So this is where we came. So a starting point for the this perspective from the soft robots. Then we take the second step for the soft robotic. It would be the soft hand. So we basically try to shrink and make things more accurate and more precise. And we move forward with our soft hand. Here you can see in this case, for example, for our soft hands, it's more, let's say, smaller, so it can be used in the application. This is another example that we had 2 years ago with a mobile robot, a ball that can move around, and with the soft hands that could, for example, help the human, I don't know, bringing an apples or grabbing a bottle. And as you could see that we also take it a bit to second steps. It wasn't only the hands, maybe in the video was a bit visible. We also add the tactile sensor using that glove. So then we were able to kind of feel which fingers and with how much pressure has been used. And we added also vision systems and a camera, as you could see also in this image, that helps for the positioning, object detection. And this was basically the basic idea behind. Then, so as you can see that so that's what I mentioned before I go to the bionic for education. But basically, you could see that we started from prototyping in the topic of the soft robotic, inspired by the nature from two perspectives. One perspective, we have the idea that, okay, we want to solve some specific problem in industries. And then like a top down, then we try to find the solutions to it using the soft technology. Other way also, we got inspired from the nature bottom up. So we really were not aiming from very beginning. For example, that has also happened to some of our animals. It has not been designed to really be used for a specific application from very beginning, but it's more inspired by the nature. And later on, once we're developing it and we're realizing actually this is a good technology, it can be used also, for example, for food industry or anything else, we were using it. So this for now, so I think I will not go more in details on these topics as is not very much relevant in the today discussions. But so giving us all this technology that we have been developing for many years, we had two challenges. One challenge is that like material and technologies that we had to develop, and we keep going developing and collaborating with different universities and different researchers. Other challenge is that how can we scale this? How can we make this that it can be sustainable? So we make a business model behind it so we can actually fund these projects and continue developing the technologies. And one area of interest that since 2019 we enter to it is in education. So we realize that actually soft robotic and soft materials are not very easy at the moment to be used in industry, because in industry you have a lot of let's say heavy objects and a lot of requirement that need to be satisfied, but the soft materials are not yet in that level. So the soft materials often breaks, they cannot hold very heavy objects, and this make the at least soft technology less attractive to the industry applications at the moment. So this is the current moment based on our experience, but of course there is ongoing a lot of research, and some of the projects are actually used in industry, but not in the level that we are expecting, not yet. Then we thought about it, and we realized that one really good area we could contribute, and this is also the topic of today, soft robotic for humanity, is education. So soft materials, as we talk about it, it has this advantage of safety. So we can easily bring them to the school with the kids. And this is where we move forward at the moment. Then I will not play this video because then it has a voice and then doesn't make any sense to have it there. So I go to the next slide. Yeah. So this domain, we enter to the secondary education, and also vocational education with the topics of the combining science and technology and engineering and art and mathematics to actually teach all these in one kit or in one development package. This is a well-known technique. So I'm not from educational background, but we have colleagues from educational background that helping us in this topic. And we very soon realized that actually bionic and soft materials has really good potential in these topics or this module of learnings. First of all, they are from the nature. So they are basically inspiration from the nature, and they combine various topics. So they combine the technology, they combine the material science, they combine mathematics and everything together. So this sounds very, very promising in terms of education. And we actually got also a lot of good feedback in that sense, both from the teachers and from the students. So it's a lot of engagement involved during such project. For today, I will introduce you two of our projects on this topic. And we have a third one, but I think for now we go with the two of them. So one thing we built very quickly was this educational kit. So we built basically a package that you could have a components for building a 3 soft robot, a fish, and an elephant trunk, and like this gripper. And yeah, we pack them together. We shipping them to the schools, and the students can now use this, and a bit like a Lego if you think about it, but for the soft materials. They can set up, and then there is also training materials for teacher to follow it. This was initial point, so it was from the hardware part, and it was amazing. We're getting a lot of good feedback, at least in Germany, but also worldwide. We are delivering some of these kits to different universities for research and to different schools for training. And then that's what I talked about the scaling. So compared to the soft materials or soft projects for the industry, in the education, we see the scalability. Therefore, we can invest also more money and more resources to it. So now we started to add digital technology to this soft material. So people could, for example, students can use a white printed posters and try to do some interactions with these environments. We build, this is similar basically as, like, if you think about it like an Lego. We build also different learning materials that the students could use their tablet or their mobile. Teacher the same, they can take a step-by-steps and learn how to make things correct and go forward with it. As I think the main, at least, approach for us here, this we took it from the, let's say, hardware perspective first, but the second is that we could see that the hardware alone is not enough. So then we start to add a different, like, say, gamification to the systems. We add now virtual reality as well to this, so then the students can use their tablet or phone to play with this setup. So it wouldn't be only just, okay, one time I set up this and I'm done what I'm going to do next, but there will be also some game behind it, and you can try to mix with mixed reality, virtual reality, and digital, and then make all this together to be a fun experience. I think I will not go through all this due to the time, but you could imagine that such systems helping students, basically they will have a hands-on, they learn from really basic things like, I don't know, screwing and two piece together, to more creativity part that they would be able to be creative. I will go forward with the topic of creativity next, but this actually give us a lot of opportunity now to develop more and more tools around the soft robotic, digital tools. So as an example here, the hardware stayed the same, nothing has changed, so we're still shipping the same hardware, but of course we are adding more and more skills or digital skills to this platform. For this case, with the collaborations, we are actually building tools that there are the CAD files. Maybe students can even do the 3D printing, laser cutters if they have in their schools for the more advanced students, and try to change something in the systems as well. So this is where the new opportunity come for us. In terms of creativity, we didn't stop there. The second project I would like to share with you was the bionic flower. So this is a flower also inspired by the nature. If you touch the sensors, it actually open or close based on the light as well. And here also students has more choice to actually a little bit change the setup and the shape of the flower. Again, similar way as previous topics, it's as a package, it will be sent to the school and the students could interact with it. We have a hardware, right? And now we added more software to it. So we wanted to students also use learn programming. So with again collaborators, we start to build some systems that the students could do some programming, simple programming with the flower. And yeah, we see that this is one path for us to contribute more in the domain of the soft robotic and bring this to everyday basically life. And we felt that one right direction is education, and with the secondary schools, and hopefully we can take this to second steps later on to the higher educations, and then we will see what happened, because of course students are the most creative people, and we get always feedback from them and teachers for the next kit or for next tools that we should develop. And with this perspective, we can also maybe later again come back to the perspective of the industry and see where it can be there. So this is more or less all for my talks. I try to keep it short and maybe give a time to the people to ask the questions. If you have any question, I will be happy to answer. Thank you.
Thank you, Shahram, for the presentation. I don't know if there are some questions here or online. Otherwise, I think I am just curious about why do you think soft robotics? So what were the main problems of trying to implement soft robots for industrial applications? So according to your experience, what do you have any specific points what it was missing on these soft robots developments?
Yeah. So from at least what we learned, there are two major parts. One is the robustness of the material. So it requires a lot of maintenance. When we apply, for example, of a soft arm in the industry, and they need to, let's say, operate something million of times, this still is not feasible. So it happened that after some number of iteration, they breaks and you need to change them. And due to the structures that the arm or at least the tooling that we have, the maintenance cost is really high. So somebody has to order, some engineer has to go and change, for example, those blower or something inside these systems. And that is one thing that it's always stopping us to scale. And the second thing was more about the material. So we did not yet figure out a good way to make the system to be strong and for a high payload applications. So when we want to, for example, hold or pick something very heavy, we have very, let's say, high challenge there. It's either the things get very heavy and it's not anymore soft and become very hard, then it's not the same as we wanted. Or then if we keep it very soft as in a soft arm or soft hands, then the tool or the device is not strong enough to, for example, hold a few kilos of the object. So it would be more for topics of very lightweighted systems.
So thank you for the answer. I think now we have other problems to add to our list for research.
Yeah, sure.
So I don't know if there is another question. Otherwise, we thank you, Shahram, for the presentation again.
Thanks.
For now, I think I will ask our next speaker to share the screen. We wanted to have a speaker as a meeting city, but unfortunately, he has been a little bit busy at the moment. But thankfully, Dr. Ziyu, who is working at the same institute, Max Planck Institute, he will give the presentation regarding miniature medical robotics application.
Yep. Okay, thanks for the invitation and introduction. So I'm going to share my screen now. So sorry for not being able to attend the workshop in person, but today I'm still trying to present our recent work on various miniature medical robots inside our human bodies. First of all, I'd like to give you some examples about the current miniature surgical robots that are used in clinics for minimally invasive surgeries. And these robotic systems are usually designed to revolutionize our traditional surgical tools that are usually dangerous and scary. And here are many successful stories. Perhaps you already know the Da Vinci system from Intuitive Surgical. And it is basically a robotic arm system that can do laparoscopic surgeries, which you can insert many small cameras and tools from some small holes into the human body to perform minimally invasive surgeries. And this system has already become a very golden standard in minimally invasive surgeries, and more than 6 million laparoscopic surgeries have been performed since 2001. And then you can see many other surgical robotic systems, including the needle insertion systems for neurosurgeries, the robotic arm for radioactive focused X-ray surgeries, the bone milling system, and the robotic system for active catheter control. And of course, you can see the robotic systems are designed to collaborate with the doctors rather than replacing them. And you can also notice that because a human is very complex, so it is quite challenging to design a robotic system that can work everywhere inside the human body. However, if you look at these robotic systems, you will see they are all tethered and very bulky. So we want to bring some new features to our future medical robots. First of all, we want to take away the wires and cables connected to the robot bodies. And we hope that we can make these devices and robotic systems to be tetherless so that we can control the robots and devices with more freedom. And we also want to shrink down our current robotic system to fit the small gaps and spaces inside the human body. So our final goal is to shrink down the robotic system to down to 100 micrometers in length scale. And the traditional robotic systems for medical applications are usually rigid. So we also would like to show that it is necessary to make the robots and devices to be soft for safety issues. And we also want to show that by utilizing the flexibility of the material, we can achieve many different interesting behaviors that cannot be achieved by traditional rigid designs. And traditional surgery was conducted one time. So that means if you have a problem, you open the human body and solve the problem all at once. However, if the problem repeat again and again for multiple times, you have to redo the surgery. So that's why we want to keep the robot in our human body to redo the surgery at the time we want. So various soft miniature medical robots can be used to reach hard to reach and high risk areas inside the human body, like the